Good afternoon. I'm Helen Robinson, the president of the Geo-Institute. It's my privilege today to introduce our 2025 Shamsher Prakash Award and Lecture recipient, John McCartney. John is a professor at the Department of Structural Engineering at the University of California, San Diego. He holds the Hal Sorensen Endowed Chair and serves as the director of the Engelkirk Structural Engineering Center. They host the NEARI Large High-Performance Outdoor Shake Table. According to Bradley Keeler, director of the Geo-Institute, after visiting the shake table last month, he was all shook up and thought it was truly rockin' and groundbreaking. But back to John. He received BS and MS degrees in civil engineering from the University of Colorado Boulder in 2002 and a PhD in civil engineering from the University of Texas at Austin in 2007. Coincidentally, I heard that in 2003, he drove an entire soils laboratory from Boulder to Austin. Not to be direct, but the sheer stress of that trip classifies as a lot of pressure, but apparently he was undisturbed. When consultants prepare technical proposals, often we're limited to 1 or 2 pages for our resumes. I know it's different in academia, but when I saw John's resume, it's longer than most of our $2 million proposals. But as I reviewed this body of work, what stood out to me was the variety of topics in which John has exhibited expertise. Just to list a few, he's the co-editor-in-chief of the journal Computers and Geotechnics. He's the chair of the GI Committee on Unsaturated Soils, and he's also the vice chair of the new task force on energy geotechnics. He received the IGS Award from the American Geosynthetic Society in 2018 and the Crows Medal from ASCE in 2012. He also authored over 160 journal papers and 166 conference papers, and I wasn't surprised to see that John is an Eagle Scout. A little bird, let's call him Zorge Hornberg, told me that in 2007, John lost a bet and ended up sporting a mohawk. So maybe tonight at the Louisville Slugger Museum, someone can take a swing at getting the scoop on that. A little bit about the namesake of this award. I had the pleasure of meeting Dr. Shamsher Prakash many years ago. In addition to his expertise in soil dynamics and geotechnical earthquake engineering, Professor Prakash developed a program of inner peace and happiness and a signature workshop on yoga, pranayama, and meditation. He's a beautiful, gentle soul. I did not feel as passionate as Brady Cox did last year to practice Professor Prakash's many yoga poses, but maybe John did, we'll see. The Shamsher Prakash Award and Lecture is presented annually to a younger geotechnical engineer, 50 years of age or less, for outstanding research or professional practice contributions in the area of geotechnical engineering or soil dynamics. John is being recognized for his outstanding contributions to understanding the dynamic and thermo-hydromechanical behavior of unsaturated soils and geosynthetic reinforced soils in transportation and energy geotechnics applications. Given his name, I was thinking about throwing in a Beatles joke, but I decided to let it be. Congratulations, John.
Thank you very much, Helen. Okay, I was told not to press the button with a big X on it. I won't do that. So I'm very happy to be here today talking to you about a lot of the work that I've been working on with my research team over the past 20 years or so. Hopefully, I'll give you a good cross-section of how complex unsaturated soils are and how important they are to consider in practice. I'm very inspired by the legacy of Professor Shamsher Prakash, and I'm very honored to give this lecture in his name. One of the things that impressed me the most about his career is his important focus on case histories. He hosted several conferences on case histories and brought together many people working on these topics. In particular, my presentation today is focused on unsaturated soil mechanics, and I think that this is a field that could really benefit from new case histories. One of the issues is that unsaturated soils have many, many couplings between them. I hope that you'll appreciate some of those through this lecture today. And being able to predict those is tricky, and sometimes we could do it, sometimes it doesn't work very well. But having case histories that show us how the soil is behaving gives us a ground truth, helps us confirm our predictions, and build confidence in our designs. So I'm very grateful to receive the award in Professor Prakash's name. So I'm going to talk about 5 different topics today. I know that's a little bit ambitious, and we're following the presentation with a visit to the baseball bat museum, so I'll make sure that I get through all of these in time. I kind of chose these topics because they start with some coupling that builds complexity as we go through. I think that these are also topics that are at the frontiers of geotechnical engineering. They're very challenging problems that that we need to put together many types of techniques to solve. So the first, geosynthetic capillary barriers. This is what I first started working on when I was a PhD student with Professor Zornberg. And this kind of inspired me to look at how water flows through soils and how it interacts with the different materials in the systems. And then that brought me on to looking into seeing how the water affects the mechanical behavior of the soils. So looking into the compression of unsaturated soils to high stresses and looking at their behavior during earthquakes, a topic of seismic compression. Most recently, I've been working a lot with geothermal energy and heat exchange, and I've been trying to look at ways that we can use heat to improve soils. We can take heat from sources like solar energy, inject it into the ground, and improve the behavior of our geotechnical systems. And now the most complicated one are the buffers for nuclear waste repositories. These are very complicated soils. There's coupling between the thermo-hydromechanical aspects, and they're also expansive. So hopefully we'll go through all of these and talk about how we can use case histories to better understand these problems. There's a lot of challenges with unsaturated soils. I see it as a big opportunity. It's a lot of fun to study these problems. The first are water flow problems. We'll talk about this with the capillary barriers. The soil and fluid properties change over orders of magnitude. We have different materials that are going to interact in different ways. And water can flow in different forms. It can flow as a liquid, but it could also flow as a vapor. And we need to then understand how water flow is going to be affecting the effective stress in the soil. Similar to saturated soils, effective stress is a average term that we use to capture changes of mechanical behavior. But in addition to looking at the effective stress, the yield stress is critical in unsaturated soil mechanics. And the yield stress can change with temperature, with degree of saturation. And if you have wetting and drying, you could have even more complicated effects on top of that. And then coupling is another very important issue because heat transfer processes, water flow processes, and mechanical processes are interconnected, both in terms of the governing equations as well as the properties that we use to quantify these responses. So talking about geosynthetic capillary barriers, this was a topic I started working on during my PhD at University of Texas. These are used as alternative landfill cover systems. They're very interesting because they're trying to mimic the natural soil layer where water comes in via infiltration and it is removed later by plants. One interesting thing that we're seeing in some early experiments is that if you have a geotextile separation layer at the bottom of the soil layer, water will not go into that until it becomes, the soil above it becomes fully saturated. So we wanted to explain how that happened, and that got me involved with physical modeling, and I'll show some results of those, and started my interest in unsaturated soil mechanics. One of the most important things with unsaturated soil mechanics is the definition of the soil water retention curve. There's many different techniques, and all of them have different features. With unsaturated soils, water can flow either by liquid or vapor, and usually we're going to push or pull on either of those phases. So if you want to pull the water out of the soil needs to have a continuous liquid phase. So this axis translation technique and hanging column technique require those aspects. But we could also use a technique where we control the relative humidity of the water vapor in the soil, and that requires a continuous air phase. So they're kind of complementary to each other, but two different mechanisms. We also worked on developing a centrifuge permeameter where we can actually mimic the infiltration processes that we may be seeing in these cover systems and use that to determine our hydraulic properties. So talking about how hydraulic capillary barriers work, usually you have a cover layer of soil on top of a coarse-grained material, which in this case is a geotextile. If your soil is compacted into place, it's usually going to be initially dry. And you can see the blue arrow tells you the initial suction in the soil. The soil water retention curve is shown on the left. And at that same suction value, if you look at the figure on the right, this is the hydraulic conductivity function. I was warned not to have any log-log plots, but one other challenge in unsaturated soils is that parameters vary over large orders of magnitude. So hydraulic conductivity, you can see, can vary over a large range, and suction, which is the energy state in the soil, can vary over a large range. So if you're at the blue line there, maybe at 100 kPa, the soil, which we think of as a low permeability material, actually has a higher hydraulic conductivity than the nonwoven geotextile. The nonwoven geotextile is full of air, and that means it can't conduct water. So in order for the water to flow from the soil into the geotextile, that overlying layer of clay needs to become wet. You have to move up the soil water retention curve until you get to the green point where your hydraulic conductivity between the two materials is equivalent. And we call that breakthrough, when water starts to flow from the soil into the geotextile. So this was a complicated problem, and I was a student, and I wanted to understand how it worked. So this is back in the phase of my career where I painted everything burnt orange. This is from Texas. I think maybe if you visit Professor Zornberg's lab, you can still see some of the burnt orange facilities. So in this, we had a layer of soil on top of a geotextile layer. We had instrumentation at different depths to measure water content and suction, and we rained water at a constant rate and collected the outflow from the bottom. So these are some typical results that you can see. So this beginning stage where we have transient infiltration, the water is moving down through the soil, and suddenly it reaches the geotextile, and you would normally think that it would just travel into the geotextile because the geotextile is a very permeable material. We use it as a filter, as a drain material, but because of this contrast in pore size, water starts to build up on top of that, and you can see it gets wetter right above the barrier layer, and you have an increase in water storage in that area. So this is an example of using physical modeling to understand how the water process is flowing through the soil and how we can understand the increase in water storage. I also had the privilege to work with Professor Zornberg on geosynthetic capillary barriers in the field. This is the Rocky Mountain Arsenal in Denver, Colorado. They wanted to build one of these evapotranspirative cover systems, and they wanted to test to see how it works first. So they put a geomembrane barrier at the bottom, and they wanted to collect all of the water that came down to the layer of this geomembrane. So then they put a geotextile on top of that to act as a drain. So even though they weren't hoping to create a geosynthetic capillary barrier, they created 4 of them instead. There were some challenges with the data from this site because it got struck by lightning several times, if any of you have been to Colorado. So my first paper that I wrote was correcting this water content data, and we saw some interesting results once we filtered that out. So at the ground surface, it was getting wet and dry. It's changing as the atmosphere is interacting with the soil. But then, as you go a little bit deeper, there's some moments in time where the soil starts to get wetter. And when you go deeper down in the soil, you see that it even gets wetter than that, almost fully saturated. So this is kind of mimicking what we saw in our column tests, where water starts to flow in, we have a unit gradient, and then starts to build up at the base. And fortunately, because Colorado is a very arid place, evapotranspiration removed the water, so it was able to recover after that. So it was very interesting to see this in our physical models, but when we wanted to try to predict it, it doesn't work very well. So you can see the numerical modeling results on the right. You see some spikes, but they're in the wrong places. You're having changes of water content near the surface, but not deeper in the soil layer. So there are these preferential flow paths where maybe water was able to go deeper than we can predict using a continuum-based model. So there's still problems to solve on this topic. This is just showing that over time, these covers are storing water during the rainy season and removing it during the dry season. And over time, they're behaving relatively well. If you look at the water balance that you can get from the moisture storage, you can find that the very little percolation, so very little amounts of water went through the base of these cover systems. So it works pretty well. We decided to keep doing some additional tests to see if you could get these cover systems to recover. So we did some mini column tests where we measured the periods of breakthrough, and then we dried the soil out and tried it again. And it was very repeatable. So even if we do have breakthrough and water gets through the system, it's going to be able to recover over time. So a few takeaways from this first topic. Laboratory and field scale testing are critical to interpret the behavior of near surface soil layers under atmospheric boundary conditions. We can use the different principles of unsaturated soil mechanics to make these covers work. But it's very important if we want to try to improve our numerical simulations in the future to measure hydraulic properties using the flow processes that are happening in the field. So if we're having infiltration and evaporation, you want to use the tests that are having those same pathways in order to have the right properties that are matching what's happening in the field. So that was my first encounter with unsaturated soil mechanics. One of the second ones that I started working on in University of Colorado when I went back to start my career in academia was the behavior of unsaturated soils under very high stresses. So I wanted to take some of the things I learned from this first case history and put it together on this. We're looking at a project for ONR on buried explosions. So these processes can happen very fast, but fortunately, one of the key parts of these the solutions to these problems is the backbone curve. So it's just your quasi-static compression curve of the soil. Most geotechnical problems only go up to about 10 MPa. In this case, we were going out to about 70 MPa. So we're able to see how the soil behaves under these conditions. And unsaturated soils can have a very major effect on the behavior of the soil in these cases. So the first thing that we need to use is the effective stress. The nice thing about using effective stress in unsaturated soils is that you can integrate the soil water tension curve into the definition of the effective stress. And you could potentially use this to capture the changes of effective stress during wetting and drying. So that's the first component that you need to look at mechanical processes. We're using the soil water retention curve to model infiltration and evaporation, but now we're also using it to represent our stress state. So it's very well established that the shear strength at failure, you get an increase in the apparent cohesion of the soil as it starts to dry out. And if you were to interpret that shear strength versus the total normal stress for different suctions, you'll see that everything lines up onto a single line using effective stress. So effective stress is used to capture changes of shear strength at failure, but people haven't had a lot of luck applying effective stress to compression problems. And that's because suction also has an effect on the yield stress. Back in the 1960s, there was a big controversy about using effective stress to model the compression of unsaturated soils. This plot here from Nasser Khalili, if you were to load two different soils, one that is fully saturated you'll see that the saturated soil yields at a lower stress and follows this lower branch. If you took the same soil but loaded it while it was unsaturated and at some certain point wet it, you would think that the suction would go down and the effective stress would also go down and the soil should expand on the elastic rebound curve. However, because suction has an independent effect on the yield stress, it causes that unsaturated curve to collapse downwards, and you collapse down to the saturated curve. So until you start to accept that you need to use both effective stress concept and the yield stress concepts to capture unsaturated soil compression, you're not able to use this unsaturated soil mechanics in effective stress to capture the compression response. So we started from that perspective, and we started to look at the behavior of soils when you load them to high stresses. So first we would apply some initial suctions to the soil and then start to load it out. So we do see this increase in yield stress as the soil gets drier. But one interesting thing we wanted to look at when we go to high stresses is that you can squeeze all of the pores and get rid of your air. This is the case of a drained compression where the air is allowed to escape. And at some certain point, your compression curve needs to converge with the saturated soil. So we can call that pressurized saturation. And the slope of your compression curve for unsaturated soils should always be inclined back towards the saturated curve. This is the concept of the yield stress load collapse curve. So as your suction increases on the y-axis, the yield stress increases and the soil gets harder and harder as you go out. There's different equations that have been used to capture this in terms of net stress or in terms of effective stress. And then this is just showing how the degree of saturation is going to be increasing. It's very tricky to track the degree of saturation in unsaturated soils, but if you don't measure this, it's not going to be very easy to apply the effective stress technique. So in these cases, you can see the soils are initially dry, and you compress them up to high stresses, and you reach this pressurized saturation technique state. So we decided to do some compression tests to high stresses. We came up with an isotropic loading cell. And these are some of the results that kind of match the cartoon that I showed you with an increase in yield stress and a convergence to the saturated curve at stresses less than 10 MPa. When you go out to higher stresses than this, things get a little bit weird. So the bi-log linear model that we usually use in geotechnical engineering is not going to work very well when you go to high stresses because things get squished down. So if you look at the curve on the left, it doesn't seem right from the geotechnical perspective because it looks like the curve is getting steeper and steeper, but this is the effect of the log plot. So log plots are always a little bit scary. But if you look at the natural scale on the right side, you can see that these curves are tending towards a constant void ratio, which we can call void closure. These are drained compression tests where we keep the suction constant throughout the compression stage. We could also do undrained compression tests. This is probably more representative of what will be happening during a fast loading case. So in these cases, the water is not allowed to leave. You have air still in there. And when you pressurize this, the air can dissolve into the water. So this is another interesting part about unsaturated soils that makes things complicated. And you can see that there's a steep decrease in the void ratio up to a certain point, and then it follows the compression index of water once you get to this high stress. So we're getting pressurized saturation without allowing the air to leave. We're dissolving the air into the water. And we can use some techniques like Hilf's equation combined with Henry's law to predict this pretty well. But then putting the undrained and drained together, it's interesting to see that you have the saturated curves on the either side. The saturated curve under undrained compression is basically compression of water. And then the saturated curve for drained conditions is the softest state. And if you have undrained conditions on a very dry soil, it's going to be very close to the compression of a drained soil. We tried to put our results into the context of the literature. We went and reinterpreted some of the results from previous studies in terms of effective stress. And we found that the trends that we were expecting from our conceptual model held for most of the soils. Our suction stress at yield increased with suction. Our effective stress increased at a different rate. You can see that usually the yield stress is increasing at a faster rate than the suction stress. And the virgin compression curves were generally either vertical or inclined, so we're going back towards the saturated curve. So most of the soils in the literature, we're going to call those collapsible because they have a greater increase in the yield stress than the increase in suction. One other tricky thing that we've looked into, but I think is still a topic for future research, is the role of hydraulic hysteresis. So I mentioned that the soil water retention curve is not unique. We have a drying path and a wetting path, and we want to integrate that soil water retention curve into our effective stress equation, but we can have two paths for that. And when you compress the soil, either under drained or undrained conditions, you could potentially start to change your soil water retention curve as well. So on the drained case on the right, you can see that the soil water retention curve is shifting upwards as you compress the soil. So you need to take that into account when you're quantifying the effective stress. Or in undrained conditions, you're going to be following some sort of a scanning path. So there's a lot of potential still on this topic to make further advances. We want to make sure that we integrate our soil water retention curve into our stress state. We want to make sure that we consider these independent effects of suction on the effective stress and the yield stress. And all soils become saturated when you load them to very high stresses. Okay, going on to the third problem. So now we had quasi-static loading. When you live in California, you have to work on earthquake-related problems. So I decided to get interested in the concept of seismic compression. So this is the settlement of unsaturated soils during earthquake shaking due to void collapse. But this effective stress that is present in the soil actually tends to provide a restraining effect to prevent the soil from settling as much as it would want to. So you have a positive effect of the unsaturated side where the capillarity is preventing the soil from collapsing, but you also have a lot of air which is able to collapse during shaking. We need to very carefully consider the drainage conditions that we're expecting. If you're doing everything very slow, then the water has time to leave, and your soil water retention curve could change in a similar way to what we saw during the static compression. But if we have fully undrained cyclic shearing, you're going to be wetting the soil along a scanning curve, and you're going to be moving up, and the rate of increase in suction on these scanning curves could change based on the initial conditions. The tricky thing on these tests is both the air pressure and the water pressure could change during cyclic shearing. So this is a topic that many people have worked on in the past. During this cyclic shearing, the voids that are filled with air are going to be softer, so they're going to collapse, rearrange, and densify. The pore fluids in the soil are going to pressurize during undrained shearing. The suction is going to be the difference between the air pressure and the water pressure. So if you have differential pressurization of the two fluids, you're going to have changes of suction. And the soil could start in a relatively dry state, and as you start to collapse it, you're going to be reducing the volume of voids, so your degree of saturation is also going to go up. So we have suction changes, degree of saturation changes. Together, they're going to make the effective stress change, and we know that our shear modulus is going to depend on the effective stress. So a lot of interesting things going on. So the first thing we studied was the effect of suction during wetting and drying on the dynamic soil properties. We modified one of Ken Stokey's devices to test unsaturated soils. And we came up with some trends that showed that the shear modulus is not only going to depend on your effective stress, but also on the yield stress. So if you wet and dry the soil, you're going to have a plastic hardening of your yield stress, and you have a permanent increase in the shear modulus of the soil. Then we wanted to maybe try to come up with some equations to predict the seismic compression of soils. So together with my student Majid when I was at University of Colorado, we came up with an empirical methodology that took data for compression of dry soils during earthquakes and post-liquefaction reconsolidation of saturated soils. putting them together into an additive equation with some features to incorporate unsaturated conditions, we came up with a prediction of our seismic compression as a function of degree of saturation. So validating this is very complicated. We did centrifuge testing, and we took the concepts from our soil water retention curve testing with in the centrifuge permeameter and applied it and just shook the soil after we reached steady state infiltration. So we were able to reach different initial degrees of saturation, and we got a pretty good match in the funicular regime. When we got to the wetter conditions, there's some scaling issues with the pore fluid, so we didn't maybe get a very good capture there. And also, there could be post-liquefaction recompression that we didn't accurately capture. So one of the challenges with that empirical methodology is that there's many parameters, and changing one of them has major effects. So we wanted to keep going back to the drawing board and redevelop this. So we went and developed a cyclic simple shear device where we could control the suction. And in these tests, we could have fully undrained conditions. We could track the changes of water pressure, air pressure, get the suction. We know the change of volume, so we can get the degree of saturation, and put all of these together to understand the role of the initial degrees of saturation. So we got kind of a smile shape in the volumetric strain as a function of degree of saturation. And then we wanted to model this. So we took our results from the UBC sand model, and we adapted it to consider the impacts of unsaturated conditions on the shear modulus, which is basically the slope of your stress strain curve. And we were able to get pretty good trends. We had to first predict the changes of degree of saturation based on the amount of volumetric contraction. And we used Boyle's law to figure out our changes of air pressure. And then we had a model that looked at this scanning path of the soil water retention curve to figure out our changes of suction and water pressure. And then we updated the shear modulus on each cycle of shearing and compared that with some of our experimental results and got a relatively good match. There's still a lot of potential to improve this more in the future. So takeaways from this topic, we're able to capture the transient trends in the seismic compression in the funicular regime, although when you go to large numbers of cycles, it unfortunately stops behaving so well, but we believe that we're in the right direction on this topic. So switching gears now to temperature, this is my main interest in my research. So one of the things I worked on with my students is trying to take heat from sustainable sources and inject it into the ground, not only to store the heat so we could use it later, but also potentially to have a benefit on the geotechnical properties. So in these concepts, you take heat throughout the summertime, usually, inject it into borehole arrays. These can either be vertical or horizontal. And then in the winter, you would extract that to heat your houses. And these systems work. One of the coldest places I've been to is this Drake Landing in Canada, and they are able to provide 98% of their heating from this borehole storage system. So our goal was to put these into the vadose zone, so the zone of soil above the groundwater table. So even the Drake Landing site I just mentioned on the previous slide is in saturated glacial material, and you have groundwater flow. So whenever you have groundwater flow, it's going to be taking the heat away from where you're wanting to store it. So in the vadose zone, you have very little groundwater flow. You do have some infiltration and evaporation, but the soil here has lower thermal conductivity, so it's going to have lower heat losses. And one of the challenges here is that now you're heating the soil. It's actually going to cause the soil to dry, and we have some additional coupled processes that we need to consider. So the first thing we decided to do is make a physical model of this. So at UC San Diego, you can see in the background of the lower left figure our shake table facility. I was able to acquire a small area of land. We drilled boreholes 50 feet deep, put an insulation layer, and then collected heat from solar thermal panels and injected it into the ground. We were able we only did tests for about 6 months, but we're able to increase the ground temperature about 12 degrees Celsius, which is relatively small, but if we continued to heat the soil, the water that we were injecting to the ground was 90 Celsius, so we could have gotten to higher temperatures. So that was a positive trend, that we could figure out how to heat the ground using sustainable sources. Now we wanted to see how that would potentially improve the ground. So one interesting thing that we found from some coupled heat transfer models is that when you heat the soil and cool it, you could have a potential permanent response. So the water gets driven away, but when you turn off the heat, it doesn't come back towards your heat source. So we came up with the idea of thermal improvement, where we're heating the soil, driving the water out. However, now there's some additional effects of this heat on the behavior of the soil. So heating is causing the soil to dry, it's making the suction increase and making the soil stiffer, but heat also affects the yield stress in a different way. So it causes a softening. So now we're having competing effects of heat on the yield stress, and we need to see which one is winning. So we haven't built a full-scale model of these in the field. We've done some laboratory cases, but if you had a geosynthetic reinforced structure, you could put your horizontal heat exchangers there or an embankment and drive the water out of these systems. You'd need some approach to prevent the water from coming back in if you have an infiltration system. But our first goal was to understand how this thermal improvement would work. So there's two ways that soils can be improved with heat. The first is when you heat them, they could potentially contract and get denser. Second, the effective stress increases, which makes your strength and stiffness go up. But we need to make sure, you can see in this figure that as you dry the soil, the yield stress is increasing, but as you go to higher temperatures, it's getting softer. From most of the data that we've seen, the positive effect of suction is greater than the negative softening effect of temperature. We've looked at very high suctions as well, going up into the megapascal range, because when you're drying the soil, you're probably going to go to a very dry case where your degree of saturation is less than 10%. So there have been relatively few studies on dry soil like this, and we do see that there is an increase in shear strength in these conditions, and the effective stress principle still applies. Thermal volume change is also very complicated. We can come up with some elastoplastic techniques or some accelerated creep techniques. But then our goal here was, again, to do some physical modeling. Let's see how this works when we put all of these systems together. So this is one test that Melissa, who introduced the session, helped me with when she was at Colorado. We just had a horizontal heat exchanger. We circulated hot water through it. We caused drying. You can see the temperature on the top and then the degree of saturation on the bottom. So we had a relatively narrow band where the soil got drier. And then we did some plate load tests. So heating the soil to different temperatures, allowing this flow process to happen, and then loading it, we saw that there was a stiffening response. We also wanted to see, could we apply this to deep foundations? So at University of Colorado, we have a centrifuge. We can look at the impact of unsaturated conditions on the compression curve. So we made some mini energy piles there where we had heat exchange loops inside of your concrete foundation, put it into a tank of unsaturated soil in the centrifuge, spun it up, and heated the pile to different temperatures, and then we loaded it to failure. So this is something that could be pretty challenging to do in the field, just due to the scale and the number of tests necessary, but in the centrifuge, it's a feasible technique. So the interesting thing we found is that when we heated the pile and allowed the soil to dry around the pile, we had an increase in capacity. So we can see that Davis's criteria can give us the capacity changes. And we also monitored the water flow, so we saw a drying effect. Predicting this is not easy. We need to use coupled heat transfer and water flow models. In this case, we're having the governing equation for all these processes that are coupled together. If you have a change of temperature, it causes a flow process, and this is where you're having coupling in your governing equations. And we also have coupling in our thermal and hydraulic properties. Calibrating these, we sometimes need to do physical modeling tests on the soil in order to calibrate the parameters. So in order to predict our undrained shear strength, our pile capacity value changes with temperature and suction, we had to do an additional test where we had a thermally induced drying of a soil. But once we had our model working, we could predict what was happening right at the soil-pile interface, and the drying effect did lead to a substantial increase in effective stress. And predicting our shear strength from that effective stress, we're able to predict the increases in pile capacity effectively. So I think that this is a technique that hasn't been used in the field, but we've done the laboratory demonstrations to get it working. So this project actually leads into the last topic today, where we have heating of soils, but this one is on bentonite buffers. So at the moment, the United States does not have a repository for storing spent nuclear waste from commercial applications. They did a lot of study on this Yucca Mountain facility that you can see on the top right. However, due to political reasons, they've stopped the investigations on that site, and Department of Energy is actually collecting data from countries in Europe who are doing repository testing. One interesting thing that people are looking at internationally is that if we do have a repository, it's probably going to be a constrained space. So we need to put the waste canisters closer together, and when you do that, suddenly the temperatures that could be induced by the radioactive decay of these materials can reach 200 Celsius. Normally, when we want to dry soils, we put it in an oven at 110 Celsius, and it dries out. But due to the complex behavior of bentonite, you could have a zone that is drying out, but have a saturated material that is keeping the drying process in the middle. So it's very tricky to predict this. We need to use our flow, heat transfer, and flow equations that we developed for thermal improvement and apply that to a deformable material. One of the reasons that we want to model these is that when we're getting the permit for one of these repositories, you need to extrapolate its behavior out over tens of thousands of years. So if you have the heater in the middle, the heat is moving away from it. These are usually buried deep below the ground, so the water pressures in the host rock could be very high. So you have hydration from the outside. So you have a wetting from the outside and a drying from the inside. And as you're having globally constrained conditions, so the soil is not able to change in volume overall, but it could change locally. You could have drying near the heater and shrinkage near the heater and expansion near the outside. So these are the new fun thing to predict. There have been some studies here, but in most of the cases, they use relatively simple models, hydraulic properties that are measured at room temperature to predict what's happening at 200 Celsius. And the predictions are not horrible, but when you're trying to extrapolate this out for tens of thousands of years, there could be challenges. So the first thing we decided to do was look at the saltwater retention curve that was developed by Ning Liu. This is a very nice equation that tells you the water retention mechanisms due to capillarity and due to absorption, and look at some of the key points along that curve and see how they're affected by temperature. So it's well known that temperature affects capillarity. It changes the surface tension of the soil and the liquid-water contact angle. So we do see a small reduction in the water content at water retention at low suctions due to this capillary effect. The mean cavitation suction is the point where you change from capillarity to adsorption, and there are some equations that we can use to predict those changes as well. Those are mostly related to the maximum absorption water content. So now we need to go back into clay mineralogy, and we know that the diffuse double layer, which is telling about how water is bound to the particles, is dependent on many issues, the cations, the valence, but also temperature. So we found that as the temperature increases, you have an increase in the size of your diffuse double layer or your maximum absorption water content. But going beyond that, you start to have a decrease. So in order to do these at high temperatures up to 200 Celsius, we have to do everything under pressurized conditions. So we had to develop a little pressure cooker that we're testing our soils in. Next, the maximum suction, when the soil dries out to the very highest suction, is also affected by temperature. And when we put all those together, we come up with a very long, big equation. And you can see the effects of temperature on this lower right figure. They don't look very much, but because we like to plot things on log scales, those are actually pretty substantial changes of suction. So we're working now on trying to validate these hydraulic properties under high temperatures. As I mentioned, when you dry the soil out at a temperature above 100, it should go to 0. But in these repositories, you can have superheated conditions. So in this case, we need to have a pressurized chamber that is acting like a pressure cooker, where when you heat it up, you can have still liquid and gas, but in superheated conditions. The water doesn't boil because it's under a high pressure. So when we do this, we can use this vapor equilibrium technique and measure the soil water retention curve at temperatures above 100. So this is going to be interesting when we finish these tests. One problem with bentonite is everything takes a year to get each point. But then going back to physical modeling, we wanted to see how these coupled processes work. They are doing some field tests in Switzerland, but it's very slow to get the data, so we wanted to replicate these in a lab situation. So we had a layer of bentonite, we constrained it and applied a stress to it, and we had a central heater where we applied 200 Celsius and also hydrated the soil from the outside in. And with this, we can track the transient loops of the soil water retention curve. So the soil gets wetter first as a wetting front moves past the sensors and then dries out. And it matches pretty well with the retention curve that we defined. And then going into hydraulic conductivity, this is usually mostly relevant for nearly saturated conditions, but we can add in these effects of temperature onto that parameter as well. Thermal conductivity does not depend on temperature, but it does depend on the shape of the soil water retention curve. So we can get the data from these physical model tests to validate our hydraulic and thermal properties. And right now we're working on trying to simulate these using tough flak and COMSOL. And the modeling is not perfect. One of the challenges is that the volume change as a function of distance across the bentonite layer, but we're getting relatively good trends. You can see on this top left figure the density variations. We're getting contraction near the heater and expansion near the boundaries. And our most recent results, we're trying to heat the soil to temperatures above 100, and when we're at low temperatures, the soil expands, but at higher temperatures, there starts to be a transition point where the soil starts to contract. And these are under high stresses, so you're not necessarily desiccating the soil, but you do get a reduction in volume near the heater. Okay. So some key takeaways from this topic. This is a very coupled problem, not only hydromechanical, but also the swelling of these materials. So some final comments, trying to tie together these 5 different topics. It's very important to accurately quantify the soil water retention curve using a technique that uses the same flow process encountered in the field. We want to understand the effects of hydraulic hysteresis pathways on a given problem, because we could have permanent hardening of the soil. We want to understand how suction and degree of saturation can affect the effective stress, but also the apparent yield stress, and then understand how that has subsequent effects on the compression response or the shearing response. We need to carefully consider the coupling between the thermal hydromechanical processes and properties. And I hope that I showed, as going through these 5 complicated topics, that it's critical to perform physical modeling experiments to really understand what's going on and check the predictions that we're getting from our numerical simulations. And I recommend to the geotechnical field as a whole, keep collecting data from case histories especially involving unsaturated soils, so that we can continue advancing this field. So I have many great students that I've worked with over the past 20 years. I tried to make sure that they're all pictured in these different group photos. And I'm very grateful for support from National Science Foundation, ONR, PEER, and Department of Energy. So with that, thank you very much.